All right, let's get into the real meat and potatoes of this unit, electron configurations. So what are they exactly? They're ways in which electrons are arranged in their orbitals. So this is actually a numerical or written or graphic representation of how these electrons fill in the orbitals and fill in the energy levels for each element. We tailor them specifically to the element in question. So the way you fill these out is based on three rules: the off-ball principle, the Pauli exclusion principle, and Hund's rule. So the off-ball principle states that electrons have to fill the lowest energy level first before they can start moving into orbitals in higher energy levels. So for example, if I'm dealing with helium and I know it has 2 electrons, I can't just say, oh, I'm going to put 1 electron here and 1 here. That's not the way it works. So this is wrong. What you can do is put them in the very first, the lowest energy level. So I could put 1, 2. You have to fill up every orbital that is as low as possible before you start moving up to the higher orbitals. Hope that makes sense to you guys. The second is the Pauli exclusion principle. So only 2 electrons can occupy the same orbital. So that means in every box, I can only put 2 electrons maximum. They can't hold 3, they can't hold 4, it's 1 or 2. That's the maximum. So the second part has to deal with how these electrons fill the orbital. They must have opposite spins. So spin is just a quantum property, so it has to deal with the type of particle that electrons are and how they behave. So think of it as one electron is spinning clockwise and the other is spinning counterclockwise, and that will just help eliminate some of the confusion. So you can't have 2 electrons spinning in the same direction in one orbital. For example, this one here, that's wrong. We can't have 2 spinning clockwise or spinning up. You always have to have one spinning one way and the other spinning the opposite way. As you can see here, no matter what, when you have 2 electrons in there, they're always spinning in opposite directions. And the last rule is Hund's rule. This says that electrons fill each orbital available before they start to pair up. So this doesn't really help when we're talking about the s orbitals, since we only fill 2 electrons in those orbitals. But it does make a difference when we're talking about the p orbitals. Those can hold 6 electrons, but remember, every orbital can only hold 2 maximum. So we have to have 3 different orbitals to complete, or 3 different boxes to completely fill up the p orbital here. That would allow me to get my 6 electrons in there. So instead of just filling in all of these boxes, let's say I've got these 3 boxes for my 2p orbital, and I want to fill in 3 electrons there, I can't just go 1, 2, 3 because of Hund's rule. It says that you have to fill in every single orbital before you can start pairing up. So what would really happen is, if I have 3 electrons, I'm going to have 1 going up in every single orbital of that p orbital. So once they've all filled in all the possible boxes, then you can start pairing up. So if I have 5 electrons, after I do these 3, then I can fill in my last 2 going in the opposite direction. So you can see that presented in this bottom picture here. Do not pair up right away. You have to do 1 electron per orbital before you can start pairing up. So just to give you a nice graphical explanation of these orbitals, the s block happens to be these elements here on the left. and little helium way over there. The p block is all of these electrons or elements here. The D block is all of our transition metals, and the F block, all of our F orbitals, is this bottom one here, the lanthanides and the actinides of our inner transition metals. And this will help you when you're actually starting to do these electron configurations to know, oh, I'm in the 2p orbital because I'm in this particular row and this particular area of the periodic table. So this is a good picture to keep and to keep reference of. I'll erase all that for you if you guys want to take a screenshot of it. So let's actually do some examples of these electron configurations so you know what to do and how to do them. So let's start with hydrogen. So this has to go back to what we've been working on this entire time. In a neutral element, in a neutral atom, how many electrons does hydrogen have? Well, hydrogen has an atomic number of 1. That means it has 1 proton. Well, in a neutral atom, the number of protons equals the number of electrons. So that means we also have 1 electron. So to do the configuration, I would just enter one little arrow pointing up in the 1s orbital. Now, if I want to do that without using boxes, we can also write this as 1s1. I have the 1s orbital and I'm filling it with 1 electron, one lonely little electron. So let's go to helium now. Helium has an atomic number of 2. This means it has 2 protons. So that means in a neutral element or neutral atom, it has to have 2 electrons. So we fill in our first electron, and our s orbitals, remember, can hold 2 electrons. Our p orbitals can hold 6 electrons. So I can put one more here in this box for the 1s in this orbital, but it has to go in the opposite direction. The spin has to be opposite. All right, so then for this one, we would write 1s2 for our configuration. Now, lithium has an atomic number of 3. That means it will have 3 electrons. So we'll fill in our 2 for the 1s. And then I have a third. That means I can jump up to the next energy level, the 2s orbital, and fill in my 1 little electron there. So the way I would write this, I have a 1s2 and a 2s1. That means I've completely filled my 1s orbital. It's completely full, and I only have 1 electron filling up that 2s orbital. Now let's jump ahead a few to carbon. Remember, carbon has an atomic number of 6. This means it has 6 protons, which means in a neutral atom we have 6 electrons. So how would we fill this out? Well, we first need to completely fill our 1s orbital with 2 electrons. Remember, that's the maximum number that each box, each orbital can hold, and they have to have opposite spin. So I have 2 down, 4 to go. Next, I need to fill in my second highest orbital. I have to always go in order. I can't just jump ahead to later orbitals. So here I also fill in 2 electrons with opposite spin. That puts me at 1, 2, 3, 4 electrons. I have 2 more that I have to fill. So we're finally getting into this 2p orbital here. Now, according to our rule, I cannot put both in one box. Remember, that is completely incorrect. I have to fill in 1 electron for every orbital before they can start pairing up. So that means the way I'll write this is 1 electron in my first box and a second electron in my second box. Now I have 1, 2, 3, 4, 5, 6 electrons total for carbon, which is what I'm supposed to have. So how would I write this configuration? 1 2s2, 2s2, and 2p2, because I only have 2 electrons in my 2p orbital. Now for nitrogen, this has an atomic number of 7, so 7 protons and 7 electrons. We can start filling these in. 1, 2, 3, 4, 5, 6, 7. Remember, I only put 1 in every box, and then I can double up. So if I had 1 more electron, I could have started doubling up in my 2p orbital here. So I would write this as 1s2, 2s2, 2p3. Oxygen has an atomic number of 8, meaning it has 8 little electrons. So we can do this all over again. 1, 2, 3, 4, 5, 6, 7, 8. Now I can start doubling up here because I've filled in 1 electron in each of my orbitals. Now is the time that I can start doubling up and adding that second electron there. So I would write this configuration as 1s2, 2s2, 2p4. And our last one, fluorine, this has an atomic number of 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I would write this as 1s2, 2s2, 2p5. So when we're looking at the transition metals and doing their configurations, we have to notice that there is something strange going on here. So if we're following along and we get to this block of elements right here, we have 3p, then we jump to 4s, and then 3d. So the 4th energy level actually starts before the 3rd energy level finishes. So you have to be very careful when you are doing your configurations that you don't just start writing 4D for any of these electrons in this or elements in this area here. The 4D is 1 level lower. So you'd be talking about an electron in this area. So this is something to pay attention to while you're doing these configurations. So let's do an example. All right, so we're going to be doing 3 examples here: iron, manganese, and calcium. So what I want you to do is to actually grab a periodic table and have it in front of you while we're doing this. That way I don't have to jump back and forth between slides for you to see the periodic table. Iron is going to be in the 3D block of our transition metals. Same with manganese. Calcium, though, is an alkaline earth metal, so it is actually going to be in the 4s. So let's get started with these. So iron is, as I said, in the 3D block, so that means we're going to probably be filling up 1s, 2s, 2p, 3s, 3p, and 4s in order to get to that 3D block. So let's see if that's the case. Iron has an atomic number of 26. That means it's going to have 26 electrons. So let's get started here. 1, 2, 3, 4, 5, 6, 7. Now once they're all full, I can add the secondary spin for those 3. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18. Now I am going to pass through my 4s, so 20, 21, 22, 23, 24, 25, 26. So that would be how I would fill in all of those orbitals. So if I'm writing the configuration, it would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then we jump back down to 3d6. All right, let's move on to manganese. Manganese is actually one before our iron, so it's going to have 25 electrons. So we're going to be filling in all of these orbitals in the same way that we did for iron, filling in all of one spin before we add the secondary spin. But if we have one fewer electrons, we're at 20 at this point, so I have 1, 2, 3, 4, 5. That's how I would end up writing that configuration for filling in the orbitals. Now, writing the full configuration here, it's 1 less than iron, so I'm still doing the same thing. 3p6, I pass through the 4 s's to get to 3d5. So that's how I would write those configurations for my transition metals. Now, calcium, as I said, is an alkaline earth metal, and its atomic number is 20. That means it's going to have 20 electrons. So it comes before iron and manganese. So that means we're not going to be getting into this transition metal block at all. We will be stopping at the 4s where calcium is found. So in this case, we'd count out our 20, 2, 4, 6, 8, 10, 12, 14, 16, 18, and 20. And that makes sense because it is the second in our 4s orbital area. When I'm writing this now, it'll be 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s2. I've completely filled all of that up, and I'm not getting into these 3d orbitals at all, so I don't even need to write 3d for that part. Now, as you could tell, that got very repetitive, and there tended to be a lot of repeating the same things over and over. So scientists always like to look for faster ways of doing things, and with configurations, we have one. We can do noble gas configurations. So what you do for these types of configurations, you find the most recent noble gas. Remember, that is the group on the furthest right hand side of the periodic table. Helium, neon, argon, krypton, all of those. And you start your configuration by citing the most recent noble gas that you've passed. So if you're talking about magnesium, or let's do calcium since we just did that one. So for calcium, if you're still looking at the periodic table, if you go backwards back into our 3p orbitals, we will hit argon as our most recent noble gas. So I would just write argon in these little brackets as my starting point. Then you continue your configuration from that point forward, which in this case only happens to be 4s2. If you have ones that go beyond this, it does make it a lot faster. That way you're really only writing the 4s's, the 3d's, and maybe even your 4p's, and that's it. So it really shortens these by a lot. And that's all that I have for you guys. So make sure you do your homework and do some practice with those, and I will see you soon.